to that one and talking about RMS values of sinusoid signal. So practically, if our signal source, either voltage or current, is sinusoid, basically we can now also calculate what is the effective value, so-called root mean square value of the signal. And this actually comes very handy when you have AC signals on some power equipment. For example, AC outlet 230 volts, what it actually means. So this value is actually calculated for sinusoid, so that what is the voltage which the voltage which provides the same power in resistor, both in well, either as a sinusoid, that's original, or what is the corresponding DC power which produces the same amount of power in the in resistor. Okay, and this is quite important, since actually this is the root mean square value, which is the also what is given for any AC voltage. So that 230 volts AC outlet actually means that the root mean square value of that voltage. So so practically I haven't given any reasoning for behind that one, but I will just draw you something here. Where does it come from? It actually comes from this calculate the power over resistor, if it's sinusoid, or the average power over. So we have this integral one, or the, let's just cut some corners here, over one period, and that was ut times I t dt. That's the average power formula. Quickly just wrap it up. So we have basically U equals I times R if we have a resistive circuit. So we have I times I times R, resistor circuits, or Z in general. But anyways, if the either current, or actually this is also the same as 0t U t times ut divided by R dt, the same stuff. You have that kind of formula, and then having a sinusoid here. Sinusoid, sine squared omega t divided by R dt. This actually, the integral over the one period for sine squared is same as, and from 0 to t is becoming u0 squared divided by 2r. Okay, u squared. All right, so, or I square times r, like that. Okay, if our sinusoid has, okay, the amplitude of u0, so the amplitude squared divided by 2r, or current amplitude squared times r divided by 2. And the same, that one would be the same as the corresponding RMS power over the same resistor. Okay, same resistor, which practically means that our URMS is same as the amplitude divided by 2. The same thing also for that for the current. So that's the RMS value, tehollisarvo. Okay, where do you use this one? For example, at 230 volts. That's AC. Actually, it means that it's RMS value. U0 for that one is actually 230 volts times square root of 2 is roughly about 315 volts. Quite high. Peak, that's amplitude, which means peak to peak of 630 volts. When you think of these values here, they kill you if you don't respect the AC outlets. Okay, that's one of the use where they use this these RMS values. Another place was when I was cut off, I think, way before that one was where I have the audio amplifier, Japanese model of audio amplifier. And there we have the directly to loudspeaker. I don't care about these. What else? There are the filters. And there, for example, 8 ohm impedance on the loudspeaker. And we want to drive 10 watts. 10 watts. Well, it's a resistance, and there's the amplifier. So basically, this is same as U times I, or actually U squared divided by R. This is power, so actually this is actually the RMS value of the signal. Basically, then we have 10 watts divided by, multiplied by 80 ohms equals U square. And there U equals, that was around, not 80 ohms, but 8. Yeah. 8, which is 80. U is same as square root of 80 and volts, which is roughly 12.6 volts. No, that wasn't the 12.6 volts. That was the 8 point something, 8.9, yeah. This is 8.9 volts, which sounds okay. So about 8 volt signal will give you 10 watts in 8 ohm. That's fine, except the signal amplitude. It's that URMS multiplied by square root of 2. This is 12.6 volts, meaning that the signal here must actually be between 12.6 and minus 12.6 volts. Meaning that power supply actually, or the amplifier must be able to generate that one, meaning that at some point the operating voltage of the amplifier must be at least plus minus 12.6 volts. Okay. So that kind of things you need to consider when you are dealing with sinusoid signals. The amplitude, actually, you need quite a lot of amplitude to have some real power on with the sinusoid signals. Okay, and namely basically all the audio or the processing kind of things. You need to consider those signals as sinusoids. All right. Then about reactive power. That was talking to myself. Yeah, I had so great time, talking to myself. Reactive power. So with a capacitor, uh, we don't have any actual power. I already told you that, okay. There's no power consumption. There's no power consumption elements on the capacitor. It charges and discharges. It charges and discharges the same amount of energy. It doesn't disappear. It doesn't vaporize in ideal capacitor. So the capacitor actually, the physical formula for how capacitor works is the topmost there. It tells that the current flowing through the capacitor is directly proportional to capacitance and the change rate of the voltage. So that's just time derivative of the voltage. And if the voltage is sinusoid, okay, then it has amplitude U0 and the angular frequency omega. Then you just derivate that one by t time, and then you actually get the current equals it's that capacitance. Okay, the larger the capacitance, bigger the current. Also, higher the frequency, bigger the current. So remember, if the omega is 0, then it blocks the current flow. So the DC doesn't flow through the capacitor. And then it has the cosine instead of sine. Okay. Another way of looking at this one is that, okay, again, capacitor is a battery. It can be charged and discharged. The blue line there is the voltage, and then the red line is the current. And this is the 1/4 of the sinusoid voltage that charges the capacitor here. So practically the capacitor is at the beginning it's empty, voltage is 0, no, but actually when you start with this quite a rapid slope of the U, just charging with the fastly changing signal U, then the current jumps very high. So it's basically it's proportional to the rate of this. And here at this point, the voltage change rate is high. It means lots of current is going there, charging the capacitor. And basically then it when the voltage on the sinusoid curve, it basically peaks here. Then the change rate is 0. The voltage doesn't change anymore. So the battery does not take current anymore. So it's fully charged in one sense. And then when you start going on the line again, on the U line down, basically then you are starting to discharge the capacitor. Okay, so 90-degree the phase shift. There's a lot of stuff here. Current, there's a 90-degree phase shift compared to voltage. Yeah, so it's 90 degrees behind of the current of the voltage. So current falls behind. As you can see, when we are here, then the current is actually, is the advance? I never get this right. Oh, actually, it's opposite. Yes. But anyways, so there's a 90-degree phase shift, U and I, meaning one is sine, then another one is cosine. And the previous picture was the first quarter of this one, quarter phase, or the quarter, and the wavelength. Oops. So we are quite close. Then basically the average consumed power. Here I have the picture of instantaneous power, which is just multiplying U and I. And that comes as a sine 2 omega t. And it goes up and down, meaning at this place here, positive, we are charging the capacitor until it reaches this highest voltage. Then at this part, actually, we are discharging capacitor. And basically, it's just continuous charge, discharge, charge, discharge, charge, discharge. But the energy does not go anywhere there. It doesn't, the electric energy is not consumed, which means that the real power, average power over one full cycle is zero. So no power loss in capacitor unless it has non-ideal parts like internal resistance on it, as the components usually have. Wow. Same way, reactive power inductor. Voltage over inductor is directly proportional to the current change rate. Looks quite similar to the capacitance, but instead of instead of the derivative of voltage, we have derivative of current, and that actually derivative of current produces or induces a voltage change which is proportional to this inductance. Same way, input voltage, sinusoid, then it's that same equation, and in order to calculate what is the current, we need to integrate, and integrating sine will actually end up giving minus cosine, and then you have this omega again, omega outside as a divider, not as a multiplier as earlier, which actually shows that okay, with low frequencies, zero frequency, we cannot have any voltage, because otherwise with zero frequency the current would go infinite or minus infinite actually. Anyhow, if you have some frequency signal, then it shows that lower the frequency, more current. Higher the frequency, less current. Okay, so it blocks higher frequency current for passing. Same stuff what we actually got the other way around on our RL filters. And similar to the capacitor, we have again the phase shift between the current and voltage. 90-degree phase shift. Now it's just to the opposite direction. And instantaneous power is the same stuff again and again. Calculate the average power, the real consumed power. There's no power consumption on inductor either, except that is made of wire conductor which has its internal resistance. By the way, one fun fact, you can make a perfect inductor using superconductors. With superconductor, actually, it does not have any resistance because the electrons are actually tunneling through and with the tunneling there's no energy loss. So in very, very low temperatures you may have a perfect inductor. I think physicists like that when in CERN and places like that. Anyways, so no power consumption in capacitor, no power consumption in inductor either. And I think, yes, that was the theory part. Sorry about that break of the of that. Wait a minute. Break of the Zoom at the middle. Let me go a little bit now at the end, some details about the fifth exercise. This could be a little bit bigger, I think. So fifth exercise, which is exercise about the AC circuits. And the first part actually is the circuit analysis of two-way speaker, which I had on my slides. And on slides, let's see. There I have this two-way crossover filter, and I changed also the corner frequencies already on the material. So now they are correct. So first part is to find the correct place on your information and calculate theoretically the values. What is the capacitor C1 value if the corner frequency of the filter is SSS? Okay. And the same frequency corner frequency for L1. And those are direct, calculations, and there you have the all values. So not a big deal. A little bit more challenging is the third one, which has the total load impedance seen by the amplifier. Okay, so what is the impedance? What the amplifier actually sees is impedance between this terminal and ground. For me, it looks like they are inductance in series with the resistance and capacitance in series with the another resistance, and those look like they might be parallel. What do you think? Okay, so that's pretty straightforward. Then, of course, more than 30 years ago, 35 years ago around, when I was studying in university, I was actually really keen on electronics, and I went to ask a question from one of the professors there, electronics, and asked, okay, what do you think if my design? I had my own amplifier design schematic, and showed that one to my supervising professor and asked, what do you think, does this one work? And he said, Antti, electronics is an experimental science. Go to the laboratory and try it yourself. The same thing actually in here. So part two, when we have the first theoretical part, Okay, that's how you calculate things. How you design is theoretical. You base the design on theory, but then you have to verify your design. Then you go and do laboratory experiments, and we have this this Tinkercad environment, and here what you should do there. First, create this circuit with the values what you found on Tinkercad. So inductor in series with the resistor and capacitors in series with another resistor, and then connect those in parallel and run the function generator as your signal source. Okay, and then basically what you do is the similar kind of measurement what I did, but actually, well, then you put two oscilloscopes to measure voltage over the this lower frequency resistor and higher frequency resistor. Well, those are loudspeakers. But anyways, the model for this is a resistor. Don't use the loudspeaker what they provide in Tinkercad. It does not really work, and it just slows down this exercise. So okay, so you're measuring the voltages over the both loudspeakers, and initial settings for the function generator are this, and for the on these oscilloscopes you need to find the basically time scale yourself. But anyways, what to measure? First, measure the signal amplitude over loudspeaker at different frequencies. Okay, that's 20 to 20 kilohertz. The whole audio range you measure on the voltage over the both of the elements. It's only about 9 frequencies, and you just mark those in a table and pay attention to this one. This frequency is your corner frequency. What you should see on the corner frequency is just about the equal signal on both lower and higher frequency the loudspeaker. If they are not roughly the same, then you did something wrong. And then, of course, on lower frequency, you should get higher signal on this over the lower frequency the speaker, and vice versa on the higher frequencies. And this is just plain measurements. Okay. And there's a hint to adjust the oscilloscope time per division setting when you are changing these values. Otherwise, take a look at this. It's actually, again, 3 decades of frequencies. If you don't set the times setting correctly, then the simulation goes really, really slow. If you see something like this, that's not good. So you adjust so that you get few of those full waves there. Okay. Next, calculation. Based on the previous the measurement, you calculate the power consumed in loudspeakers. You can also use the same, just expand that table there if you wish. But anyways, you will just do the calculation. You have measured the signal, okay, in volts. It's probably peak to peak. Pay attention to what you are measuring there. Okay, let's see, for example, this one. If you are simulating it, the simulation. The oscilloscope, oh, it doesn't really show it here, not too well. The oscilloscope here shows the full range. So full range signal is here from, well, it's 2 volts, the full range. So this actually is about 1 volt signal. So it's about, this is 10 boxes. So yeah, that's about 1 volt signal. On the other hand, this is hard to read also. So on the Tinkercad, you should actually tweak a little bit of the time scale. But on this simulation, I cannot do it. I don't want to tinker that one now. Okay, but anyways, calculate the power. Haha. What power? AC power, which meaning RMS power. That's the power is consumed in the loudspeakers. Translate that value, from, which is peak to peak, to amplitude, to RMS. Then you can actually calculate what is the power consumed in the loudspeaker. And finally, using the previous measurements, draw the power in decibel watts. Wow, you will be engineers. You should actually start using decibels for that kind of things like the signal power and such kind of things. So this is a good exercise for that one. If you want to know what is the decibel watt, basically it's decibels relative to 1 watt power. There's a Wikipedia link behind of that one. It's basically, there's a calculation formula. Decibels overall, it's always 10 times log of 10 of the power divided by reference power. And in this case, our reference power is 1 watt. Yep. And okay, there's also that logarithmic frequency scale. This is actually a so-called Bode diagram, what you are going to draw there. Again, something engineering. Let's look at my RC calculator, where you have your link. You have the link to this Excel. You can make your own copy, and you can actually then take a look how to produce that frequency scale. Or, well, frequency scale. There's another hint. I know. I was thinking, is this actually a kind of rude way reminding, okay, the one hint is Google how to plot log x-axis in Excel or some other tool what you are using. In 35 years ago, we had logarithmic paper to plot this. You don't want that logarithmic paper. You want some tool and learn how to use it. But still the presentation of this kind of pictures, when you have frequency and power, you have power in decibels and frequency in logarithmic scale, unless otherwise stated. Okay, and now there are some questions. One was about what instead of loudspeakers in we could okay, you will be using just resistor. So the model of the model for the loudspeaker for this exercise, it's same as on this model. It's a resistor. Since in principle it's a device that consumes power, meaning the natural model for it, it's a resistor. The same as a model for any power, any energy source on electronics, it's either Thevenin's model or Norton's model, mostly Thevenin's model. Okay, great. Any other questions? Okay, if you don't have any other questions, then I did stop this recording